Well, thanks everyone for coming. I want to just spend a few minutes talking about a little bit of research we've been involved in using some airborne geophysics over a floodplain up near Loxton, the Bukpinong/Clarks floodplain, where we've been interested in looking at whether we can map spatiotemporal changes over the floodplain and across the river in that area using geophysical methods. So that's the focus of this particular talk. And I'd like to acknowledge the contributions of my co-authors in helping pull this together. It's very much a demonstration, if you like, about the technology and its potential, rather than a thorough evaluation of the results we've generated against ground data and the like. So as I've mentioned, it's really around the potential of multi-date geophysical data, characterizing change across the floodplain. What's the potential of these technologies to do that? Why airborne geophysics? Well, potentially it's a method of looking at spatial patterns and spatial changes in a quantitative way, which you would struggle to do necessarily on the ground with boreholes or anything else without investing a large amount of time and effort. So we're interested in seeing whether we can use these methods to provide insight into the spatial extent and geometry of lens systems. And then, because we're looking in a temporal sense, can we look at the advance and recession of these lens systems with these sorts of technologies? And then does that provide a framework to look at how the floodplains respond from an ecological and hydrological perspective? So why airborne EM? What's the relevance of this technology in this part of the world and in Murray in particular? Well, essentially it's a technique that maps conductivity contrasts, which in the floodplains of the Murray are controlled by primarily by groundwater quality. So we're measuring a physical property change with these technologies. Why do we think about using it in a multi-temporal sense or a temporal sense? It's because we can now acquire data with different systems. We can, if they're calibrated, we can actually look at quantitative change. We can measure those changes and ascribe some quantitative parameter to them. So we now have calibrated airborne EM systems. We've also got, accompanying that, much more robust and advanced inversion procedures to handle those data and to handle the parameters that relate to the systems themselves. So when we're getting a measure of conductivity or modeling conductivity from these systems, we're getting a much more reliable output, if you like. So it's really about trying to look at the quantitative changes and the conductivity contrast. So what does airborne EM data measure? Technically, it measures a function of the electrical conductivity contrast or variation in the subsurface. Spatial patterns in the subsurface are based on changes that occur within the subsurface sediments, contrasts within the subsurface sediments. And because we're measuring electrical conductivity, we're measuring not just changes associated with the lithologies, but also changes associated with the groundwater and groundwater quality. And in the context of the floodplains, most of the changes we see as evidence, or has been evidenced more recently, is not lithologically controlled so much as more controlled by the groundwater and its quality and its variability. So our study area is the Bukpinong floodplain. As I mentioned, it's in the proximity of Loxton, just north of Loxton, and we're looking at this area here just adjacent to the actual Bukpinong irrigation area. Just flagged that groundwater flow in this area is from the east pretty much towards the floodplain in that part of the world. Our hydrology or hydrogeology, very quickly, and we're concentrating essentially on the upper part of the sequence with the airborne data. We're looking at things occurring and changing and varying in the Monument Formation, the overlying Coonamble Formation, and then down just into the top of the Murray Group sediments as well. We're not concerned with what's happening up here so much as really what's happening in the floodplains in that part of the sequence. What systems did we fly in this study? We flew two systems in 2006, SkyTEM system. It's a system that was developed in Denmark. We flew it again, but with a slightly different set of configurations in 2015. So we have almost a decade of difference over that time. There are variations in the parameters that relate to these systems, but I won't spend too much time. From a geophysics perspective, that might be of interest, but to some of us here it may not be. I think the important thing is we can account for the variations in the system parameters in the way that we model and produce models of ground conductivity. So that's the new inversion methods take account of these differences. So we're not looking at artifacts arising from different systems in producing our models. We account for those in the inversion process, so the model that we generate at the end of the day is independent of those differences. So that's a useful thing, if you like, if we're actually trying to look at changes that are driven by physical changes in the subsurface. Acquisition dates, as I mentioned, 2006 in August, September, and then subsequently in May 15. And these are the flight lines over that floodplain area. You've got the two flight lines, and they roughly coincide. There are some differences because you're trying to get a helicopter to fly a towed rectangular thing beneath it exactly along a particular flight line is not necessarily that easy, so it does waver back and forth, but that's not necessarily a problem when it comes to modelling. The inversion process we employed was a spatially constrained layered earth inversion. It assumes that the conductivity variation is essentially a horizontally changing thing, not vertically driven, which is appropriate in this part of the world where our changes are essentially subhorizontal. And what we do is look at constraints along the flight line and across flight lines as well. So we're processing the data, and we did process these data, two data sets with the same inversion method, so we're keeping a constancy, if you like, in the way that we treat the data as well. And so this is a sort of example of what we get. This is just for one flight line across Bukpranong, from the irrigation area here up in the north to the middle of the floodplain here, across the Murray itself and across the Clark's floodplain here. An inverted section through that area. This is the geology of that section. This is what the inverted section will look like. It's just produced here in terms of conductivity variation. So we see high conductivities in the subsurface. This is a result of the saline groundwater flowing from essentially from the east towards the floodplain. We see around the Murray, we see a lens system developed around the Murray River itself, but sitting above a very saline or conductive groundwater system. If we look at the data for two dates, and in this case we've taken a depth interval from 4 to 10 metres, so we're dealing with essentially the Monument Formation and variations that occur within that sequence in terms of the conductivity, and we've just transformed the conductivity data to a groundwater EC value through a relationship that we derive from borehole data and borehole conductivity values and and the conductivity derived from the geophysical data. So we've got two data sets in this particular case from two different dates, but from the same depth interval in the subsurface. And if you look closely, you can see some subtle differences between the two dates. The extent of the flushstone or the lens systems around the river does differ and changes. You can see changes in that pattern. So it's suggesting there are changes occurring temporally or between those two time differences. And I'm now just going to focus in on two lines of data just to have a look at that time difference more specifically in the subsurface. So these are two lines, line one, and I'll just step back. That's this long line that runs in a sort of north-west southeast direction across the Murray here. In several instances it crosses the Murray and then up through here, a tributary coming off that, and the Murray through here. And down here we can see that it's highly conductive. Here we're going essentially across relatively fresh parts of the Murray in this sequence of sediments. If you look closely, you can see differences between the 2006 and 2015 data sets. You can see variations in the conductivity values. So in the 2006, it does appear to be fresher relative to 2015. So we're seeing quite a difference. If we actually look at that in terms of the fresher parts or components of the groundwater system, as indicated here now, so ignoring the highly conductive groundwater system, we're looking at the fresher components of the subsurface. There's a suggestion that from 2006 to 2015, we're seeing a recession or a reduction in the size and geometry and variation in the geometry of these fresh zones around the Murray. We can see, for example, we don't see that system here in this data set down here. So we're seeing that disappearing in this data set. We're seeing movements in that direction up here. So we do see quite a difference in the time sense and the reduction in the size and geometry of these flush zones around the river over this 10-year period, or near 10-year period. Going back to the second line of data, just looking at how that changes and how it might be related to hyperic zone variation. If you look at the river here, and we have a scroll plane running through here, we might have hyperic flow or intergranular flow moving through that direction. We see that in the data set, or hinted at in the data set in here. Obviously, you need to do further groundwork to justify or validate that suggestion or that model for what we're seeing here. But essentially, these data are providing an indication of the geometry and the variable patterns of these lens systems adjacent to the Murray. And this is just that same line, but again, over the two timeframes that we're looking at. Small differences observed, not as great as that longer line that we saw. So what it's suggesting is the geometry that changes and the variability that we see over the 10 years, it does vary in the lateral sense along the river. No surprises perhaps, but that's what we're seeing in the data. If you look at individual soundings, so taking data from individual points along this floodplain, so this is Clark's floodplain up here, we can see how the differences vary with depth. So this is depth for 3 points, 3 models. In this case, we see the greatest variability in the near surface here. Not much change in that part of the floodplain there, and then other changes through there as well. If we actually look at the changes in the spatial sense across the floodplain, where are the biggest changes and where do they occur? Is it a positive change or a negative change? So this is changes in groundwater EC between the two dates. This is like a difference images between the two dates. The paler colours, the beigey colours, suggest there's not much change between the two dates for this slice in the subsurface between 4 and 10 metres. But as we go onto the floodplain itself, we're seeing a reduction in the EC in the subsurface materials, and again in the around other parts of the floodplain. So in summary, we're seeing AEM responses that are a function of groundwater salinity. The AEM data does quite well define the geometry and extent of the lens systems, arguably then providing some framework for monitoring changes in hyperic zones and for studying maybe hyperic exchange and so on. There are definitely measurable changes between the two dates we've looked at. We certainly see a strong suggestion that the lens systems have contracted significantly in that time period. So we need to look at those data against existing river stage data over that time frame and other bore data. And I'd like to acknowledge my co-authors and contributors to the work. Thanks very much. So we're seeing the biggest change coming up, but we're also seeing changes in the near surface as well, which might be a response to watering as well. I think Volmer's done some experiments that demonstrate that geophysics methods can also be used to pick those effects up in the watering. Is that right, Paul?
There's quite a lot of activity that's actually happening around that site, so there's a fair bit of analysis that could be done from the existing data, and there's other complementary data sets that could be looked at. Like there's surface watering, there's SIS operating as well, which you can start to pick out the influences from that. I've actually got a question in the 2015 around that Big Bend.
Yeah.
I would have thought that maybe an impact from the SIS, a change to losing stream conditions.
Yeah, we see a very patchy change. We don't see anything substantive, and I think maybe it's on a much smaller scale spatially than might be indicated, but that's what the data is saying, so we don't see a huge change. Yeah.
One more quick one.
Did you pick up any effects from the flooding from 2010, 2012? That was almost all of that.
Yeah, it was. We haven't, whether that change we see here, where we're saying we're having fresher or a reduction in salinity in the floodplain, which would have been covered by part of that floodplain, by that flood event, is a consequence of that, I don't know. you know, that's something we would have to have a look, look in more detail at.
Thanks.
Thanks, Juan.